Forecasting is the process of making predictions of the future based on past and present data and analysis of trends. A commonplace example might be estimation of some variable of interest at some specified future date. Prediction is a similar, but more general term. Both might refer to formal statistical methods employing time series, cross-sectional or longitudinal data, or alternatively to less formal judgmental methods. Usage can differ between areas of application. For example, in hydrology, the terms forecast and forecasting are sometimes reserved for estimates of values at certain specific future times, while the term prediction is used for more general estimates, such as the number of times floods will occur over a long period. Risk and uncertainty are central to forecasting and prediction. It is generally considered good practice to indicate the degree of uncertainty attaching to forecasts. In any case, the data must be up to date in order for the forecast to be as accurate as possible. Categories of forecasting methods: qualitative versus quantitative methods. Qualitative forecasting techniques are subjective, based on the opinion and judgment of consumers, experts. They are appropriate when past data are not available. They are usually applied to intermediate or long-range decisions. Quantitative forecasting models are used to forecast future data as a function of past data. They are appropriate to use when past numerical data is available and when it is reasonable to assume that some of the patterns in the data are expected to continue into the future. These methods are usually applied to short or intermediate range decisions. Examples of quantitative forecasting methods are last period demand, simple and weighted end period moving averages, simple exponential smoothing, and multiplicative seasonal indexes. Average approach. In this approach, the predictions of all future values are equal to the mean of the past data. This approach can be used with any sort of data where past data is available. In time series notation, whereas the past data. Naive approach. Naive forecasts are the most cost-effective forecasting model, and provide a benchmark against which more sophisticated models can be compared. In time series data, using naive approach would produce forecasts that are equal to the last observed value, if the time series is believed to have seasonality. Seasonal naive approach may be more appropriate where the forecasts are equal to the value from last season. The naive method may also use a drift, which will take the last observation plus the average change from the first observation to the last observation. In time series notation, drift method. A variation on the naive method is to allow the forecasts to increase or decrease over time, where the amount of change over time is set to be the average change seen in the historical data. So the forecast for time is given by this is equivalent to drawing a line between the first and last observation, and extrapolating it into the future. Seasonal naive approach. The seasonal naive method accounts for seasonality by setting each prediction to be equal to the last observed value of the same season. For example, the prediction value for all subsequent months of April will be equal to the previous value observed for April. The forecast for time is where equals seasonal period and is the smallest integer greater than. The seasonal naive method is particularly useful for data that has a very high level of seasonality. Time series methods. Time series methods use historical data as the basis of estimating future outcomes. Moving average, weighted moving average, Kalman filtering, exponential smoothing, autoregressive moving average, autoregressive integrated moving average, e.g., Box-Jenkins seasonal ARIMA or SARIMA extrapolation, linear prediction, trend estimation, growth curve, causal, econometric forecasting methods. Some forecasting methods try to identify the underlying factors that might influence the variable that is being forecast. For example, including information about climate patterns might improve the ability of a model to predict umbrella sales. Forecasting models often take account of regular seasonal variations, In addition to climate, such variations can also be due to holidays and customs. For example, one might predict that sales of college football apparel will be higher during the football season than during the off-season. Several informal methods used in causal forecasting do not employ strict algorithms, but instead use the judgment of the forecaster. Some forecasts take account of past relationships between variables. If one variable has, for example, been approximately linearly related to another for a long period of time, it may be appropriate to extrapolate such a relationship into the future, without necessarily understanding the reasons for the relationship. Causal methods include regression analysis includes a large group of methods for predicting future values of a variable using information about other variables. These methods include both parametric and non-parametric techniques. Autoregressive moving average with exogenous inputs. Quantitative forecasting models are often judged against each other by comparing their in-sample or out-of-sample mean square error, although some researchers have advised against this. Judgmental methods. Judgmental forecasting methods incorporate intuitive judgment, opinions and subjective probability estimates. Judgmental forecasting is used in cases where there is lack of historical data or during completely new and unique market conditions. Judgmental methods include composite forecasts, Cook's method, Delphi method, forecast by analogy, scenario building, statistical surveys, technology forecasting, artificial intelligence methods, artificial neural networks, group method of data handling, support vector machines. Often these are done today by specialized programs loosely labeled data mining, machine learning, pattern recognition. Other methods: simulation, prediction market, probabilistic forecasting and ensemble forecasting. Some socioeconomic forecasters often try to include a humanist factor. They claim that humans, through deliberate action, can have a profound influence on the future. They argue that it should be regarded a real possibility within our current socio-economic system that its future may be influenced by, to a varying degree, individuals and small groups of individuals. Recent popular publications like Capital in the 21st Century are regarded as major contributors to the increasingly apparent possibility of such reality. It is argued that the influence private and public investment have on our future can never be discomposed of the individual Machiavellian human character. Such theories are generally regarded conspiracy theories. But the increasingly worrying socio-economic development in the world grants some of these theories a persistent credibility. Forecasting accuracy. The forecast error is the difference between the actual value and the forecast value for the corresponding period, where E is the forecast error at period t, Y is the actual value at period t, and F is the forecast for period t. Measures of aggregate error. Business forecasters and practitioners sometimes use different terminology in the industry. They refer to the PMAD as a MAPE, although they compute this as a volume-weighted MAPE. For more information, see Calculating Demand Forecast Accuracy. Limitations of errors. The two most popular measures of accuracy that incorporate the forecast error are the mean absolute error and the root mean squared error. Thus these measures are considered to be scale-dependent, that is, they are on the same scale as the original data. Consequently, these cannot be used to compare models of differing scales. Percentage errors are simply forecast errors converted into percentages and are given by a common accuracy measure that utilizes this as the mean absolute percentage error. This allows for comparison between data on different scales. However, percentage errors are not quite meaningful when is close to or equal to zero, which results in extreme values or simply being undefined. See also Calculating Demand Forecast Accuracy. Consensus forecasts. Forecast error. Predictability. Prediction intervals, similar to confidence intervals. Reference class forecasting. Seasonality and cyclic behavior. Seasonality. Seasonality is a characteristic of a time series in which the data experiences regular and predictable changes which recur every calendar year. Any predictable change or pattern in a time series that recurs or repeats over a one-year period can be said to be seasonal. It is common in many situations, such as grocery store or even in a medical examiner's office, that the demand depends on the day of the week. In such situations, the forecasting procedure calculates the seasonal index of the season, 7 seasons, 1 for each day, which is the ratio of the average demand of that season to the average demand across all seasons. An index higher than 1 indicates that demand is higher than average. An index less than 1 indicates that the demand is less than the average. Cyclic behavior. The cyclic behavior of data takes place when there are regular fluctuations in the data which usually last for an interval of at least 2 years, and when the length of the current cycle cannot be predetermined. Cyclic behavior is not to be confused with seasonal behavior. Seasonal fluctuations follow a consistent pattern each year, so the period is always known. As an example, during the Christmas period, inventories of stores tend to increase in order to prepare for Christmas shoppers. As an example of cyclic behavior, the population of a particular natural ecosystem will exhibit cyclic behavior when the population increases as its natural food source decreases. And once the population is low, the food source will recover and the population will start to increase again. Cyclic data cannot be accounted for using ordinary seasonal adjustments since it is not a fixed period. Applications. Forecasting has applications in a wide range of fields where estimates of future conditions are useful. Not everything can be forecasted reliably. If the factors that relate to what is being forecast are known and well understood, and there is a significant amount of data that can be used, very reliable forecasts can often be obtained. If this is not the case, or if the actual outcome is affected by the forecasts, the reliability of the forecast can be significantly lower. Climate change and increasing energy prices have led to the use of e-gain forecasting for buildings. This attempts to reduce the energy needed to heat the building, thus reducing the emission of greenhouse gases. Forecasting is used in customer demand planning in everyday business for manufacturing and distribution companies. While the veracity of predictions for actual stock returns are disputed through reference to the efficient market hypothesis, forecasting of broad economic trends is common. Such analysis is provided by both non-profit groups as well as by for-profit private institutions. Forecasting foreign exchange movements is typically achieved through a combination of chart and fundamental analysis. An essential difference between chart analysis and fundamental economic analysis is that chartists study only the price action of a market, whereas fundamentalists attempt to look to the reasons behind the action. Financial institutions assimilate the evidence provided by their fundamental and chartist researchers into one note to provide a final projection on the currency in question. Forecasting has also been used to predict the development of conflict situations. Forecasters perform research that uses empirical results to gauge the effectiveness of certain forecasting models. However, research has shown that there is little difference between the accuracy of the forecast of experts knowledgeable in the conflict situation, and those by individuals who knew much less. Similarly, experts in some studies argue that role thinking does not contribute to the accuracy of the forecast. The discipline of demand planning, also sometimes referred to as supply chain forecasting, embraces both statistical forecasting and a consensus process. An important, albeit often ignored aspect of forecasting, is the relationship it holds with planning. Forecasting can be described as predicting what the future will look like, whereas planning predicts what the future should look like. There is no single right forecasting method to use. Selection of a method should be based on your objectives and your conditions. A good place to find a method is by visiting a selection tree. An example of a selection tree can be found here. Forecasting has application in many situations. Supply chain management. Forecasting can be used in supply chain management to ensure that the right product is at the right place at the right time. Accurate forecasting will help retailers reduce excess inventory and thus increase profit margin. Studies have shown that extrapolations are the least accurate, while company earnings forecasts are the most reliable. Accurate forecasting will also help them meet consumer demand. Economic forecasting, earthquake prediction, EGA forecasting, land use forecasting, player and team performance in sports, political forecasting, product forecasting, sales forecasting, technology forecasting, telecommunications forecasting, transport planning and transportation forecasting, weather forecasting, flood forecasting and meteorology. Limitations. Limitations pose barriers beyond which forecasting methods cannot reliably predict. There are many events and values that cannot be forecast reliably. Events such as the roll of a die or the results of the lottery cannot be forecast because they are random events and there is no significant relationship in the data. When the factors that lead to what is being forecast are not known or well understood, such as in stock and foreign exchange markets, forecasts are often inaccurate or wrong as there is not enough data about everything that affects these markets for the forecasts to be reliable. In addition, the outcomes of the forecasts of these markets change the behavior of those involved in the market, further reducing forecast accuracy. Performance limits of fluid dynamics equations as proposed by Edward Lorenz in 1963. Long-range weather forecasts, those made at a range of 2 weeks or more, are impossible to definitively predict the state of the atmosphere, owing to the chaotic nature of the fluid dynamics equations involved. Extremely small errors in the initial input, such as temperatures and winds, within numerical models double every 5 days. Complexity introduced by the technological singularity. The technological singularity is the hypothetical emergence of superintelligence through technological means. Since the capabilities of such intelligence would be difficult for an unaided human mind to comprehend, the technological singularity is seen as an occurrence beyond which events cannot be predicted. Ray Kurzweil predicts the singularity will occur around 2045, while Werner Winger predicts it will happen sometime before 2030.